Continuing example 4.8, we just started looking at part A of this problem. So we need to go ahead and plug in for this equation here. So our y is 10 meters. Y naught is 0 meters. Okay, that was our initial position. Okay. V naught y we just found was 21.2 times t minus 1/2 times g, we will say 9.8 meters per second squared times t squared. Okay. Let's go ahead and rearrange this as 4.9 t squared, and I'm going to drop the units for now. Okay, minus 21.2 t plus 10. Okay, now we can use the quadratic formula to solve this. So we'll have t equals negative 21.2 plus or minus negative 21.2 squared minus 4 times 4.9 times 10, okay, all over 2 times 4.9. Now, solving this, we'll get 3.79 seconds. Okay, so that will be the time at which the ball is caught. Okay, we'll go ahead and do that. Remember that there is a plus or minus here. If I were to take the negative in this case, I would have got a negative time. Okay, so we don't have negative time in this physical case, so this will be the time we take, 3.79 seconds. Okay. Now for part B, it states what are the magnitude and direction of the ball's velocity at impact. So remember that our v naught x remains constant throughout. Okay, so that will be 30 times cosine of 45 degrees. So that gives us 21.2 meters per second. Okay, our v sub y changes, however. So let's go back to our equations here. Okay, and we can find our v sub y using this equation here. V sub y equals v naught y minus g times t. Okay, so that's what we'll use. So v naught y minus gt. Okay, so we can plug those values in. We have 21.2 minus 9.8 times the time we just found, because we're again trying to find the velocity at impact. So then we get v sub y equals negative 15.9 meters per second. Okay, now we can go ahead and solve for our velocity's magnitude. So it'll be 21.2 squared plus negative 15.9 squared, and we get 26.5 meters per second. So that is the magnitude of our velocity. Our direction is found using this here. Theta equals tangent inverse Vy over Vx. Okay, and after you plug that in, Don't forget to put the sign in here. So your v sub y is a negative value. So remember that that is important. Okay, so you'll have negative 15.9 divided by 21.2, and you'll get negative 36.9 degrees as your direction. Okay, so this is example 4.8. I want to quickly let you guys know of finding the maximum height of a projectile above its launch position. Okay, sometimes you'll be doing a problem and it asks you for the maximum height that it reaches. Okay, you can use this equation here to do so. It describes it a little bit more in the book, but I just want you guys to understand that there is an equation in order to find that maximum position here. Okay. There's also this idea of time of flight. So this is the time at which the object is in its trajectory. Okay, so we know that for this, the position and the displacement in the y direction must be 0 at launch and impact on an even surface or a flat surface. Okay, so we rearrange the equation that we just used, y equals y naught plus v naught yt minus 1/2 gt squared. Okay, so we rearrange that and we plug in the fact that v naught y is v naught sine theta naught. Okay, and we put that equal to 0. So since the displacement must be equal to 0 in this case, okay, and we can solve for t. So in this case, we'll have t either equals 0 or it equals 2 v naught sine theta naught over g. Okay, so this is t, or time of flight. Okay, oh, whoops. Okay, so this is just telling us the total time that a projectile will be in the air. Okay, so in the last one that we did, this example over here, we weren't looking at the total time of flight because the ball was caught above that surface, right? It was caught above 0, so we can't just solve for a time of flight. Okay, just erase that little bit and continue. We can find the trajectory as well. So this is found by eliminating the time variable from the kinematic equations and solving for y. So first we want to take y initial and x initial as 0. Okay, so the first way here we can find time in this equation. So x equals v naught xt. Okay, this makes sense since, I'm going to go ahead and write this, v naught x equals x over t. Okay, our initial position over time. And then we solve for t and plug in what v naught x is. That's just v naught cosine theta naught. Okay, now we can substitute this here into the equation for position. Okay, again, that's taking y naught equals 0. And we obtain this. Okay, whoops. And can continue to rearrange until we get to this form here. Okay, so this is the equation that describes the trajectory. Okay, and notice that it is in the form y equals ax plus bx squared. Okay, or it's a quadratic equation. Yeah, quadratic equation. Okay? So this describes that trajectory motion, which makes sense. Okay? All right. We also have another term called the range, and that's going to be the horizontal distance traveled by the projectile. And we can find this by considering a flat surface or setting y equals 0. So again, this would also mean that y naught equals 0. Okay? So we're saying that there is no change in y. Okay? So we take what we just had, this equation here, and set it equal to 0. And we'll get two different solutions. One of them is going to be that x equals 0. The other one will be that x equals 2v naught squared sine theta cosine theta over g. Okay? Now we can go ahead and use a trig identity here and let x equal r for range. And we get that the range is equal to v naught squared sine 2 theta over g. Okay, so these are a couple of examples of the range and how the different initial velocities and the different initial angles of the velocities will change your range. Okay, so there's like an optimal angle if you want your range to be farther, and so forth. Okay? All right. So let's go ahead and put this stuff to use with another example. So example 4.9, we have a golfer. He's got himself in two different situations on different holes. On the second hole, he is 120 meters from the green and wants to hit the ball 90 meters and let it run onto the green. He angles the shot low to the ground at 30 degrees to the horizontal to let the ball roll after impact. On the fourth hole, he is 90 meters from the green and wants to let the ball drop with a minimum amount of rolling impact. Here he angles the shot at 70 degrees to the horizontal. To minimize rolling after impact, both shots are hit and impacted on a level surface. What is the initial speed of the ball at the second hole? That's the first question. So let's go ahead and use the equation that we just learned, the equation of range. So we want to know the initial speed of the ball, so that's just going to be v naught. Okay? So if we take r, let's put a, r equals v naught squared sine 2 theta naught over g. I think that's it. Yep. And we solve for our speed here. So v naught will be r times g over sine 2 theta naught square rooted. Okay, now we can solve for our speed. So our range for this first one is 90 meters. So he wants to hit the ball 90 meters. Okay, so this will be 90 times 9.8 meters per second squared over sine 2 times the angle here, which is 30 degrees, and all in a square root. So let me go ahead and put that into my calculator. So 90 times 9.8 over sine 2 times 30. And I get my initial velocity, or I'm sorry, my initial speed is 31.9 meters per second. Okay, so we'll continue this in the next video.